Okay, so you're going to use this video today to check your answers on your review to prepare you for the Rock and Fossil Record unit test. So the unit began with a guy named James Hutton visiting us, and he is known as the father of geology, but he actually set the theme for our unit. So the first question should read like this. James Hutton believed the present was the key to the past and that a few catastrophic, which means big bad events, like the Great Flood in the Bible, didn't create all the rocks. And so you might remember he believed in uniformitarianism, that the same processes happen again and again to shape our rocks. Now, question number two is the difference between absolute and relative dating, and that's an important key concept. Absolute dating gives us the exact age of a rock or fossil, where relative shows order. Then we get to question three, which actually is a bunch of important definitions to know. So the first one there is the principle of superposition. It is a relative dating technique that says younger above older. On the next question, original horizontality, that principle says that the sediments are always deposited in flat horizontal layers in the first place. And so when we see a layer that is tilted or folded, you know that the tilt, the force that made the tilt or the fold happened later, that they were originally laid down flat. Now the next one, the principle of cross-cutting. If layers are cut by a fault or an intrusion, then the rock layer that was cut is older. What I didn't type here is the intrusion or the fault line has to be younger. The idea there is there have to be rock layers in existence first in order for them to get cut. And then finally, of the four relative dating principles, this is like the peanut in the Snickers. The principle of inclusion says this: if rock chunks, like the peanuts, are included in a rock layer, they have to be older than the layer they're in. Here's the idea. That rock chunk has to be in existence in order to get wrapped up, to get surrounded by another rock type. So the inclusion is older. I know that inclusion and intrusion are really similar. Intrusion is when magma sneaks in like an intruder. Inclusion is when you have a rock layer included in something else. Okay, now here we go back to the intrusion thing. Remember in the song we went, you can have intrusions of igneous rock. And think of an intruder as something sneaking in. So magma sneaks in and cools. And you think, could this really mess up rock layers? Yeah, it melts them. It erases what's there. Okay, our next type of possible disruption is a fault line. And this is literally when there's a crack between rocks. When rock layers break, there's still contact between them. And plate tectonics will learn way more about fault lines as we study earthquakes. Now, the next one is a fold, and that's when rock layers bend. Sometimes they look curved like a capital A, sometimes like a capital U. And then the final type of disruption we have here is a tilt. And when this is when rock layers slant. They're still straight, they're not bent, but they are slanted. So after we studied relative dating techniques, we got into absolute dating. And so to understand absolute dating, you have to understand isotopes. So notice I underlined the word same element. Isotopes are two forms of the same element. They have the same number of positively charged protons, but different numbers of neutral neutrons. Now, what do we mean when we say that there's an isotope of a certain element like that's radioactive, excuse me? It means it's unstable and it won't stay in that unstable form forever. And so carbon-14 is the unstable radioactive form of carbon. Another way to say it is it's the radioactive isotope of carbon, where carbon-12 is definitely the stable form. So our next definition is, what is a fossil? So a fossil has two requirements. You probably remember that minerals have four. Minerals have to be solid, non-living, natural, and have a crystal structure. Fossils have two requirements. They have to be naturally preserved, and they have to be evidence of life. So you probably remember my story in high school when I was making an insect collection. I was not actually making fossils because humans can't do that. Here's the catch, though. It doesn't say in the fossil definition naturally preserved and has to be the real part, like has to be a tooth, bone, or shell. So trace fossils are also considered fossils, but they're evidence of activity instead of the real part. Examples are, of course, fossilized dung, poop, and burrows, casts, and molds. And an index fossil is another category of fossil, and the key word here you must have is short. Index fossils are on our planet for a short amount of time, and so if you find an index fossil in a rock layer, that's a good find because you know what period in history, like say Jurassic, Triassic, Cretaceous, that rock layer came from. Okay, so now this is going on to the next page for you all. And so we've listed 6 ways fossils form, and this order is important. And if you didn't put them in this order, it's okay. But this goes from most common to least common. So the first way is to be encased in sedimentary rocks. Then the second way is mineral replacement. Remember, that's like petrified wood or the coprolite, when minerals go in and fill in the cell walls and replace what was there. In tree sap, which is called amber, in tar pits, mummification, remember, is drying out, and then freezing is the least common, which you're like, well, that's weird. That seems like it'd be really common. But it has to be a place that is below freezing all year round. So those are the 6 ways fossils form. Now, here's number 5. What is a coprolite? Okay, so this is the first part. It's fossilized dung. And scientists like finding coprolites because it tells you ideas about the diet and the size of the creature, right? Big animals, big coprolites. Now, what about a mold and a cast? You probably remember seeing the mold, which is a print of, in my case, it was a shell, and then the cast is the filled in mold. So here's the deal in nature. You always have to have a mold to get a cast. Like there has to be something to fill in, but sometimes a mold never does become a cast if it doesn't get filled in. And shells aren't the only things we can have prints of. You probably remember the fern fossil from our fossil exploration. That was actually a mold. It was a print of a fern leaf, and also footprints are very common. So then let's get to this geologic timescale. Excuse me, I needed a sip of Coke Zero. Geologic timescale football field. And do you remember how when you were doing the football field, you probably started to get a little frustrated as you were putting the appearance of different living creatures on the football field because everything was scrunched towards the today end zone. That's an impression that I want you to definitely have. Another thing I want you to know is the answer to question 8. Simple creatures appeared in the fossil record longer ago and more complex were recent. Humans are the most complex creature out there. And remember, we were barely off the goal line here today, the 0.04 yard line. Single celled organisms like bacteria were much further back. Um, Now, number 9 also asks about geologic time, and the right answer to number 9 is C. So here's the deal with the geologic time scale. Eons are split into eras, like Cenozoic, Mesozoic, Paleozoic, and then those eras are split into periods, like Jurassic, Triassic, Cretaceous, Devonian, and so on. So the period is the shortest span of time out of those 3. Now, what about scientists in the age of the Earth? Scientists are in agreement that the Earth is 4.6 billion with a B. Be careful on your test. I give you some options in the millions. Don't pick those. Remember, 1 yard was 50 million years. Okay, so when we are thinking about absolute dating, also known as radiometric dating, I wanted you to complete this chart specifically for carbon dating. So remember that a half-life is the time it takes for half of an unstable isotope to turn into the stable form. And so here are the only right answers for the percents. After 1 half-life for carbon-14 or any radioactive isotope, there's 50% of the carbon-14 left. Then as time goes, the half-lives go, that percent keeps getting cut in half. Now, as the percent of carbon-14 gets cut in half, time moves on. So the age of the fossil is older. So remember a half-life for carbon-14 is 5,730 years. So 2 half-lives would double that. 3 half-lives would not double the 11,000 number. You go 3 times 5,730 to get 17,190 and so on. Now, I would not have you totally have that memorized. It would be in a multiple choice format on your test. So to finish up now, is it ever possible for a fossil to run out of carbon-14? And the answer is yes. Now, that would make a scientist happy because you would know that your fossil is pretty old. But would a scientist be out of luck? And the answer is mm-mm. Instead, they would analyze that rock or fossil for a radioactive form of another element, say maybe uranium-235 or potassium-40, that has a much longer half-life. And the idea is if there's a longer half-life, it's less likely to have run out of that unstable form. Okay, and then the last thing we did in this unit was build a geologic column. And a geologic column actually makes a good attempt to fill unconformities. So when we look at a rock outcropping, say by a highway, a lot of times the layers look perfect, but not always. Sometimes they look jumbled up and there's a gap in the rock record where erosion has taken something away. And it makes us go like this, I wonder what used to be there. Well, the geologic column, like the one that you all built, it is that tool to figure out what used to be there. So geologic columns fill up unconformities. So there you go. You should be studying this review. If you deeply understand these concepts, you're going to be in good shape on your test.